Hello everybody, this lesson is going to cover the properties of solutions. It's going to go through a bunch of vocabulary that we'll be using to do some calculations in a later video. So first let's talk about what a solution is. If you remember way back to the beginning of the year, we learned about classification of matter, and solutions are way down here as a homogeneous mixture. So, when we have matter, we separate it into pure substances or mixtures. Solutions are a type of mixture. And then we separate it into if it's uniformly mixed or not, and solutions are uniformly mixed. So they are homogeneous mixtures or homogeneous mixtures. Two of the most important words that we're going to need are called solute and solvent. So the solute is the substance that is being dissolved. We often think of this as the solid that we're dumping into a liquid, but it does not have to be a solid. So oftentimes it's easiest to think about it in terms of which is the smaller amount, right? So things like salt dissolved in salt water, or sugar dissolved in soda, or you could have something like the carbon dioxide gas bubbles that are dissolved inside the soda. And so all of those would be examples of solute, and they are not all solids. The solvent is what this thing is being dissolved into. That's typically the liquid. Once again, doesn't have to be, but it usually is a liquid. So if we're looking at salt water, it would be the water inside the salt water. If we were looking at our soda, it would be the water that's in the soda. The term solution is what we call it when we have mixed the solvent and the solute together. So when they're combined together, right, that's the solution. Looking at our examples from before, salt water is a solution. Soda is a solution. We have a term called solubility. Solubility is how we determine how much of the solute you can dissolve, and it will be temperature dependent. Sometimes depending on the temperature, you may be able to dissolve more or less. There are all sorts of combos of solutions, lots and different ways you can mix things together, different phases and combinations. So you do not need to copy this big giant chart down, just look at it. I'll kind of walk through it. You could have a gaseous solution, which is either a gas mixed with a gas, or a liquid mixed with a gas, or a solid mixed with a gas. You could have a liquid solution where you have gas dissolved in liquid, or liquids in liquids, or solid in liquid. These are probably the most common. And then maybe gas and gas. Solid solutions, you could have a gas in a solid, you could have a liquid in a solid, or you could have a solid in a solid. And you can see some examples here. So, for example, air is different gases mixed together. If it's humid out, you could have water vapor. So that's the liquid in the gas. I don't know if you know what mothballs are. Mothballs are these weird little balls of something called naphthalene that they put inside like storage trunks when they're going to store clothes in the garage or the attic, so that moths don't get in there and eat up the fabric. Naphthalene smells really horrible, so if you know what mothballs are, you probably know what that smell is. So that's a strange one where you have solid and gas mixed together. Soda was a great example of gas in a liquid. Rubbing alcohol, remember everybody was clearing out the shelves trying to make their own hand sanitizer, right? Rubbing alcohol is when we take an alcohol and we dilute it into water. We have seawater, right? That's a good example of a solid and a liquid, salt water. The gas in a solid one is not super common, right? The ones with the little stars, there's not a lot of examples for. This one, the liquid in a solid with the dental fillings, that's becoming less common. People used to have silver fillings in their teeth, and now, dentistry has advanced and they're not as, commonly used. So I think in a few years, people may not know what those silver fillings are. I may have to find a different example. And then alloys. Alloys are what you get when you mix two metals or more together. So brass is an example of an alloy. Okay. All right, let's talk about the term saturation. If I tell you something is saturated, you probably have kind of a real life concept of what that might be. A lot of times people will say like, oh, I had a paper towel and I cleaned up a big mess and now it's all saturated. So saturated for us in chemistry, there's kind of three different terms that we talk about. We say saturated, where you've dissolved the most amount of solute possible. You can't dissolve anymore. It's full. It's absorbed all it can. It's dissolved all it can. Then we have unsaturated, which is when you have less than the maximum amount. And then you have something really strange where you have what's called a supersaturated, where you have more than the maximum amount dissolved. And that should sound bizarre to you. Like, how can you have more than the maximum? Well, the way you make a supersaturated solution is you heat up a solution so you can dissolve more and more and more and more and more solute. You can cram a lot more in when it's warm. Then you slowly cool it down and you don't bump it and you be very, very careful and it will slowly cool down and be super saturated. It means it's holding on to more solute at that cooler temperature than it normally would. It's very unstable. So let me show you a video that shows this supersaturated solution.
The flask contains a supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution. Focus your attention on the portion of the solution to which the crystal is added. Here is the process again in slow motion.
So what's happening here is that there's so much solute dissolved into that solution that it's very unstable. And when he drops that crystal in, it gives a place for all the solute particles to start, crystallizing around. They kind of latch onto it. And that's when you see what we call the solute crash out. So when you see all of a sudden it starts turning into the white crystals, that's the extra solute that really shouldn't be in there falling out of solution. We call it crashing out. I used to try to make supersaturated solutions to do this in class, but every time we would have passing period, people would, run up the stairs and open and close the classroom door so hard that it would shake a little bit and it would set off the solution because they're very unstable. Even vibration or a scratch in the glass can sometimes cause it to happen. Anywhere it can latch on or get shaken a little bit, you can see it crash out. All right, so next let's talk about something called colloids. Colloids are not really solutions. It's a little bit tricky because it has to do with the size of the particle. A solution can't have particles that are too big. So if the particles, the solute, are too big, then it's called a colloid. Some of the things you may think of as solutions are actually colloids. So for example, fat particles mixed into the solvent are typically colloids because fat particles are pretty big. So things like milk, whipped cream, butter, mayonnaise, those are colloids. They're not true solutions. Sometimes you may see like foam rubber where you have air bubbles suspended in the rubber. Usually those air bubbles are too big to be considered a true solution and be considered a colloid. A lot of paint and colorful glass, makeup, those color particles are pretty large, and so they usually don't count as a solution. If it's a foggy day, you're driving in your car and you can see the fog, the water vapor is always in the air, but when it's a fog, the particles are too big to be a solution. Same with things like smoke and clouds, hairspray, things like that, aerosols. Those are usually too big of particles. Next, let's talk about solubility. How do we know how much stuff dissolves? How can we change the solubility? So the solubility can be changed based on temperature and pressure. Gases and solids are going to be affected differently. So for example, if you heat up the solvent, you can dissolve more solid. Makes sense if you think about putting sugar into cold coffee versus putting sugar into hot coffee. You can get a lot more sugar to dissolve in the hot coffee. But for gases, increasing the temperature decreases the solubility. Think about warm soda. What happens to the carbonation if you have a warm soda versus a cold soda? The gas doesn't want to stay in the liquid if you warm it up. If you were to warm up your soda, right, all those dissolved gas particles come out. So increasing that temperature causes a decrease in solubility. If we want to talk about pressure changes, it's not going to affect the solid, right? I mean, the solids are not really, or liquids, not really affected by the pressure, but gases are. If you increase the pressure on a gas solution, right, you can cram way more gas particles down into that liquid. That's actually why our soda cans are pressurized, is to keep the carbonation dissolved into the liquid. Sometimes you're going to see solubility charts or graphs. They can look a little bit crazy because they tend to have a lot of different substances on one graph. I don't want to have to look at a different graph every single time I have a new substance. So we'll typically put a bunch of compounds all on one graph, so it's a little bit less work for us. So you can see here we have the temperature and solubility. As I increase the temperature, look what happens to the solubility. It goes up for these things, right? These are solids. So the solubility goes up as you increase the temperature. You can get more grams dissolved as you increase that temp. You have to be careful and look at the volume on the y-axis. Sometimes it's 100 mils, sometimes it's a liter, sometimes it may be something different. So just be a little bit mindful that you check your units. Now compare this graph to this one. Instantly, you should notice that there's a big difference here. You should see that the slopes are backwards, aren't they? Here, our slopes are negative, which means as we increase the temperature, my solubility is going down, which tells me immediately that this is a gas. If I heat it up and the solubility goes down, that is going to be a gas. Okay. All right. Now, if I give you a solubility curve, you should be able to figure out where these saturated, unsaturated, and supersaturated portions are. If you think about it, right along the line is the point at which we have the most dissolved possible. So that's the saturation point. If you're at 40 degrees, you can dissolve almost 70 grams. If you're at 50 degrees, you can dissolve 90 grams, right? So you can see where the saturation point is on the line itself. So if you have less than that, you're unsaturated. If you have more than that, you're supersaturated. So if I give you temperatures, you can kind of, use the graph to get information about how much can dissolve. If you want to make a supersaturated solution, what you would do, let's say you want to be able to get, let's say you want to be able to get 100 grams dissolved in a 30-degree solution. Well, that's supersaturated. So what you would have to do is you'd have to heat it up to at least like 55, 60 degrees, dissolve in as much as you want, cool it back down to 30, and then it would be supersaturated. Okay. Another aspect of solubility is sometimes when you have certain compounds, they're going to be soluble in water and sometimes they're not. So a solubility curve is way more accurate, right? Because when we say something's not soluble, I mean, technically, if you keep adding more and more and more water, I suppose you could get some of it to dissolve. It just, at some point, you have to have a little bit of common sense and draw the boundary somewhere, right, about what is or is not soluble. So we like to use a solubility chart. The way this works is if a molecule has any of these ions, it will always be soluble. Anything with an alkali metal, anything with ammonium, anything with acetate, anything with chlorate, anything with nitrate, anything with perchlorate, these will be soluble. Off to the side are like the little letters to help you remember. People like to come up with little mnemonics or things based on this. So AAA CNP reminds me that it's these things are always soluble. These ions will always break apart from the other ion it's with. Now, chlorine, bromine, and iodine are usually soluble. They are going to be soluble unless they are paired with one of these three ions. So, sodium chloride, soluble. Magnesium chloride, soluble. Calcium bromide, soluble. Silver chloride, nope, it's not going to dissolve. It's insoluble. Okay, it's not going to dissolve. Lead bromide, not going to dissolve. Lead chloride, not going to dissolve. Fluorine is usually soluble unless, except when it's paired with one of these. Sodium fluoride, soluble. Magnesium fluoride, nope, insoluble. Down here, these are not going to be soluble. These are insoluble unless they're bound with some of these exceptions. So magnesium hydroxide, nope, not going to dissolve. Sodium hydroxide, yes. Calcium hydroxide, a little bit, not much. We can do it. I usually have to heat it up. I have to stir it. I have to let it sit for a couple of days. It'll sort of dissolve, but not very well. One thing I do want to talk about real quick is the difference between dissolve and another word that's very similar that we should be better about distinguishing between. when something dissolves, the solute particles get surrounded by water and separated from each other. But it's not necessarily breaking apart into ions. Dissociation is when the ions have their ionic bond broken because the water gets in between and splits them apart, and then the ions are separated. You can have things that dissolve but don't dissociate, like sugar. Sugar will dissolve, the particles will spread apart, but they will not turn into ions. You can have things that dissolve and dissociate. It's like table salt, sodium chloride. The sodium chloride bond will be broken, and so that will turn it into its individual ions, and they will float around by themselves as ions now. That's dissociate. And, we should be better and more careful with our terms, and I will admit I am pretty lazy when it comes to distinguishing between these two terms. But if you're being asked a question about it, you should be able to tell me the difference between these. Related to this idea of dissolving versus dissociating is something called electrolytes. You have probably heard the term electrolytes on things like Gatorade bottles, right? It says, oh, it's filled with electrolytes. You should drink it after doing sports. And it's kind of exploiting people's lack of science knowledge. They're basically selling you salt water. Anything that dissociates, that has ions that get made, is an electrolyte because it can conduct electricity. So if you dump salt into water, that's an electrolyte. Now, sodium chloride is not the only electrolyte. A lot of those sports drinks have other salts that are dissolved, other electrolytes. But an electrolyte is not something inherently fancy, right? Salt water is an electrolyte. Compare that to a non-electrolyte, which is when we have a covalent substance that will dissolve, they will separate from each other, but they're not going to turn into ions because water is not going to come in there and break a covalent bond, right? And so it will not conduct electricity. Your sugar may be now, far apart enough from each other that you don't see it anymore. It's not a clump of sugar in your cup. It's not going to be a sugar cube sitting in your coffee anymore. But the bonds themselves have not been broken. So I'll show you two pictures that I like. All right, so one of these pictures is dissolving, and one of these pictures is dissociating. One has the substance separating from other molecules, but ions are not being formed. One is having an ionic bond disrupted, and now I have individual ion particles floating around that are surrounded by my solvent. So if you look, this is dissociating. I had an ionic substance. The water came in, started getting in the way, pulling off particles. Now I have an anion over here and I have a cation over here, all surrounded by my solvent. Over here, this is dissolving. This giant covalent molecule is not being broken into ions, is it? It's being pulled away from each other, but it's not being broken into pieces. So we just finished up our thermo chapter, right? Where we were learning about energy transfer. So dissolving and dissociating can actually have energy associated with it. We call it the heat of solution. So what is the energy transfer when you're preparing these solutions? Is it going to be exothermic and get hot? Is it going to be endothermic and get cold? Do I need to heat it up to make it form, right? Some solutions, when you make them, are so exothermic that it can be very dangerous if you go too fast. You can crack the glass, it could explode, right? You could have real problems. So knowing the heat of solution is important kind of from a safety standpoint when you're trying to mix these things together. Another thing to keep in mind is the phrase like dissolves like. So we learned in our IMF chapter, right, that polar things dissolve in polar things and nonpolar things dissolve in nonpolar things. And that can be important during this chapter, that we don't forget that. All right. Last thing is, sometimes you want to know how to speed up this process. Dissolving is not always fast, so there are ways that we can speed it up. They may be different based on if it's solid or gas. Just like before, right? Our solubility changes. So if you increase the temperature, you'll get more collisions, and so your solid will dissolve faster. Makes sense. Hot coffee, cold coffee. You could also stir it. If you stir it, you're going to expose more surface area, right? That's why when you put sugar in your coffee, you stir it around with a spoon or a little stir stick. You're trying to make it dissolve more quickly by exposing more surface area to allow for more collisions. The other thing you could do is crush it up. So instead of putting a sugar cube into your coffee, if you crush it into just regular granulated sugar, there will be more surface area exposed, and so it will dissolve faster. For gases, if you want to speed up your solution, your process, you could decrease your temperature, or you could increase your pressure. Just like before, right? I love this little picture. Sometimes people don't quite understand why pressure could increase this. Well, you're physically cramming the particles down into the solution when you increase the pressure. So you can see on these little canisters, if you increase the pressure, you decrease that volume, right? And so you're literally smashing them down in here. So that can really make things go faster. So that is probably the most vocab term heavy lesson we do all school year. I think this PowerPoint has more vocab words than probably everything else we do combined. So your key term box may be overflowing this time. You should also be able to come up with good connections because our whole life is filled with solutions, right? We have solutions all around us. So you should be able to come up with lots of good things. And then make sure you really, really study these terms, because when we do our calculation lesson, if you don't know what solute and solution and solvent are, you're not going to know which number goes where. And so you need to make sure that you're pretty good on these vocab terms before we do our calculation lesson next time. I really am not a vocab heavy teacher, I don't think, compared to like a bio class. You know, I'm not trying to get you to memorize as many vocab terms in a chapter as possible. I only want you to know the ones that are really relevant. And so this is a time where you gotta take the vocab seriously because it will impact our calculations down the road. Okay? All right, everybody, that was it. I hope that was helpful. Bye.